Okay, so let's continue. So, as I mentioned, like we were investigating these voice quality parameters and wanted to see if they're related to depression and PTSD. And so what we did, we investigated this through statistical analysis first, and we're going to talk about this, how to do these t-tests with p-values in the end in one of our lectures. But like one important aspect there is like just to remember, the lower the p-value, the more significant the difference is between the observations. And one important part is also that we didn't have statistically significant difference between men and women, because that's also often like a source of error, that you have like some bias in your features that are related to something different than the task that you actually want to solve. So how does this look like? Well, it looks like that depression, for example, has a lower NAQ value, and no depression has higher NAQ values. That means that individuals with depression have more tense voices in these interactions than individuals that do not suffer from depression. So what we tried to do then is basically take all these features and project them into some arbitrary space. And so this kind of like will look like something like this. In this case, we have 2 dimensions. So imagine that we took these 2 features that you just saw the plots for, and we project them into this space, and we try to separate individuals that don't suffer from depression from those that suffer from depression. So what we try to do with these machine learning algorithms is we try to find a discriminative hyperplane, like a line or a plane through a multidimensional space that separates these classes from each other. And what we used in our experiments were support vector machines, and you can see the support vectors displayed here, and these support vectors are the ones that basically like hold up the hyperplane. Okay, so if these values wouldn't be there, the hyperplane would be learned to be somewhere else. Okay, so imagine this value is gone here, right? Where would the hyperplane move? Well, it would move somewhat like down here, because this guy is not supporting it anymore on this side. Okay, so it would move down here, and maybe this observation here would become a support vector, so the hyperplane would go something like there. Okay, so that means like the observations that you have, they're sort of like holding this this hyperplane in place. Okay, so any of these support vectors, if you take them out, the hyperplane changes. But if you take any of these non-support vectors out, nothing changes. Okay, so they don't support it. And so this is kind of like why these support vector machines are so popular, because you only have to look at a few observations in your data once you have trained it to detect if a new observation is falling on the right or the left side of this hyperplane. So that will be signified by a minus or a plus. And so and you don't have to regard these data points down here. Another really cool feature about these support vector machines, we're going to go into this in detail in one of our lectures, is that they find the optimal separation. Okay, so they don't just find a hyperplane, because right now with these data points, like here would be also legal separation, right? Or right here, that cuts off this perfectly as well, right? But those have problems, and we're going to get into this in more detail in the next lecture. But imagine if the separation hyperplane goes very close to one of these points, right? And your observation might not be perfect. There might always be noise in your observation, right? So a little bit of noise in one of these observations could already move this over the edge and classify it the wrong way. Okay. So what you try to do is you try to find a separation that has the widest margin. That's why we have widest margin there. This is kind of like one of the nice characteristics of these support vector machines. And this is what we did in this task, because we didn't have that many data points back then, and we wanted to see what we can come up with and how well we can separate individuals that suffer from depression and those who don't. Another important aspect here is that we did a leave one speaker out experimental testing. That means what we try to do is that we keep individuals that we want to classify or test on completely out of our trainings. That's what I mentioned in the beginning of Monday's lecture, where I said we never mix our testing and training sets. Okay, so it's very important that we do not merge them and don't overfit on our training set before we do the testing. Okay, so that is important, and in particular, if you look at human behavior, everybody has very idiosyncratic behaviors that are representative of an individual and not of the actual condition. Okay, and so that's why this is important, that you kind of have all the observations that are pertaining to one individual outside of your training set and test on an entire individual at a time. Okay. And we're going to get into more details at that. Like, this is one of the practical lectures that I mentioned, where we're going to walk through all the methods to how to validate and how to test machine learning experiments in general, like without specifying the classifier itself, but in general, like how to set up an experiment and how to evaluate it. And then, so we did this leave one speaker out testing. And some of the important aspects about like how to report a machine learning experiment are displayed here. So this is kind of like a slide that gives you an idea of like how to report machine learning experiments. So first of all, it would be good to know what the baseline is. So if you have, for example, I don't know, you go through a heap of straw, and there is one needle in it, and you have to identify if the next item that you pull from this heap is a needle or a straw, right? And so so you pull straw all the time, and you say it's straw, always straw, 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 straw. And if you say straw all the time, you are 99.999 times of correct, right? But you didn't find the needle, okay? So if you just report on accuracy, or if you just report without mentioning what the baseline is, nobody knows how well your experiment is actually doing. Okay, so it's very important to have a baseline, which in this case is chance level. So you guess if the person is depressed or not depressed. In this case, it was 50% for depression and 53% for PTSD. So your guessing is very close to just chance. So the accuracy then, if you're 75% correct, you're already improving by 25% over the baseline. So that's already pretty cool. And so accuracy is only one measure to report performance. And we'll have experiments and like examples where you will see that this is not enough. So again, in like these very skewed data sets where you have a lot of like non-target elements in your data, but you have only a few target elements in your data, accuracy is meaningless, okay? In those cases, you need something like an F1 measure. And we're going to talk about this in more detail, but F1 in general just weighs both false positive and false negative errors the same way. So it gives you a better assessment of how well you're doing in these more skewed data sets. Okay? Yeah, and this is just like a little bit of a summary of what happened. If for depression, if we ask all the questions, we get like about 75% correct. But in PTSD, the type of question that we asked in these virtual human experiments was actually the neutral questions were more important than the positive or negative questions that should elicit a positive or a negative response to the question. But that's a bit more detail that we don't really have to go into right now. Just for completion, we also worked on multimodal data, and we didn't just work on acoustic representations or acoustic assessments, but we looked at behaviors like smile behaviors, mouth movements, and fidgeting behaviors. Fidgeting behaviors like self-touches, like rubbing like your arm like this, or playing with your ear and hair. So yeah, we investigated those behaviors and found quite a number of differences in our data, but it's less important. You can go through this a little bit, but just know that the behaviors were indicative. We're reporting again mean values, standard deviations, p-values, and statistically effect sizes with this Hedges G value there, and we're going to talk about this as well. So you can you will learn how to do a nice evaluation in your own experiments, both on the feature side, but also on the experimental side. So you want to use these statistical tests to show that your features are significant for the classes, that separate them nicely, but also you want to show that one classifier is outperforming another one. So you want to do these experiments on both ends of the machine learning experiments. Yeah.
So good question. So from the very beginning, how do you guys construct this architecture? Okay, which parameters do you need to monitor?
Yeah.
And how do you train the data from all data?
So that's a very good question. So the process that we followed was the following. So first of all, we had humans interview other humans about their depression and so on. So we tried to identify what are the typical questions that people ask when you want to find out about a person that has depression. So we look at human-human interaction. And then we model the virtual human interaction based off of that. Then we go into the literature and see, okay, what are the behaviors that people have found in the past? So these are the papers from 1974, 1980. People have reported different behaviors that are indicative of depression or PTSD. And so now we want to come up with like the one machine learning experiment where we identified the global flow changes. We want to design feature extractors that get those features for us. And then we collect those. So we have now made the transition from like what questions to ask, what features to look for, how do we extract those features, and then now we're just using those features in machine learning experiments. And like a supporting machine is just one way to do it. You can use anything else, like really. So the architecture is kind of like it's a sequential process that you follow. If you would start your experiment or your machine learning approach on your own data, you would first of all like identify your problem. Like, what do I want to do? What data can I get access to? What have people thought about this data before? Like, should I look at this part of the data or should I look at that part of the data? And how do I efficiently get that part of the data that is important for my problem? And then you would experiment with different kinds of classifiers. So it's kind of like you have to identify your problem, you identify your data, what is important in the data. You can do statistical tests on that. You can do literature review. You can like inspect the data yourself and see what is important. Is there something that's just noise? Like, is one column always 0, for example? Like, that's a common issue in data sets. And then like I've seen this in so many if you use these online feature extractors or something like that, sometimes they just produce zeros on one column, and then you're like, okay, what am I going to do with this? Well, I throw it out because it's not meaningful for my problem. so there are a lot of these kind of considerations.
Also, when you mention like you input the data into apply the algorithm on data, right?
Yeah.
So you we pretty much have to identify the issue we want to resolve. For example, parameter A probably have relationship with parameter B,
Yeah.
and then we input those data apply algorithm like support vector,
Yeah.
and probably output a coefficient that tells us the relationship. So we have this, right?
Yeah, so you identify which features are meaningful for your problem,
Mhm.
and then you use those as input to your system, to your machine learning algorithm. Okay?
Okay.
So you are kind of like pre-selecting what is important, and then you train on that. So you don't want to use all data, like, so for example, you wouldn't, I don't know, like, if you wouldn't use news articles on climate change to predict, I don't know, student grades at USC, right?
Mhm.
So you would use maybe news article about like teaching quality and like the students themselves, like demographics, etc. To predict student outcomes, but you wouldn't use some unrelated information that you can access. But like, what's the relationship, right? So you don't want to, like, you focus on what data is important, okay?
Mhm.
And then you take this and put it into your machine learning algorithm, right? Okay. So these are just the number of behaviors that we had access to and we could identify for our problems, and they work quite well. So these were visual features, but then we can also use verbal features, and verbal features that were important were, for example, the positivity of responses to certain questions. Like individuals with depression had lower positivity in their responses, or it took them longer to respond to questions. They had to think about the question longer. So just as a kind of like a set of, like, as an example here, you don't, like, if you deal with human behavior, if you like reduce yourself to just one type of behavior, like acoustic behavior or verbal behavior or visual behavior, you might not see the entire picture. So there's a lot more going on. So that's kind of like what we deal with often, where we have to combine multimodal information to make a good assessment of what's going on. And I can go, we will have like a lecture on multimodal machine learning, but this is just a flavor of like what will happen. Okay? Alright, so this is just also a example summary here. And let me see, don't want to bore you too much. Yeah, so one more example on, well, yeah, let's just, I would like to give you an example of like how the voice informs us about the situation a bit more. I should have probably brought this up a little earlier, but if you listen to these two examples, so I brought some examples where an individual is giving feedback to another individual. So it's like, yeah, okay. So this is kind of like the feedback that they give.
Oh, okay. Oh, okay. Okay. Yeah.
And then this is the same individual giving feedback to another person.
Okay. Okay. Okay.
So there's kind of like a qualitative difference between those. Like in the one hand, like is yeah, okay. And the other one is like, okay, yeah. And so the question in this case is like, which back channels did the individual use when he was interviewing suicidal adolescents? And it's kind of clear that the second set was used in this context. So this kind of like gives you an idea that it's not always the person that you're investigating that you should only look at, but also the person that they're interacting with. And so that the entire context is important. So yeah, the tone of voice is very a powerful aspect of human communication. And this is just another example of how we investigated speech features to assess or to come up with a method that like identifies features of individuals that have depression. And in this case, we looked at a way to identify mumbled or slurred speech. And the way we did this is we look at formants, which are the resonance frequencies of the vocal tract, and the formants are mostly influenced by the tongue position. So you see those tongue positions there, I, U, A, and stuff like that, okay? So these tongue positions influence the sound quite a bit. Even though your fundamental frequency and your vocal folds are the same, you can change the vowels by just moving your tongue. And this is kind of like, look how this looks like, where on the one hand, so here you have the first formant here and the second formant there, but for E and for you have it down here, where they're much more closer together, right? So these changes are quite significant depending on the different vowels that an individual says, right? So you have to move your tongue. But apparently it is not as easy for everyone to do this, and individuals that suffer from depression often have psychomotor retardation, which is actually influencing their motor control. So they are not enunciating the vowels the same way as they should, and as the general population does. So what we were interested in were these three cardinal vowels that are at the extreme ends of these vowel spaces or vowel spectrums. And so we want to know how this triangle kind of looks like when we compare it between individuals with depression and those without. And to do this, we made use of machine learning again. Because if you just look at vowels and you just observe them, you might have some spurious results, and like it's a lot of data, and like you have many points of observation. So, but you want to reduce this, and so we utilized unsupervised machine learning to reduce the space. So this is kind of like one of the use cases for unsupervised learning, where you have a lot of data, but you want to only access a couple of prototypes of the data. Okay. So what we did is we took the audio, we identified when the individual was voicing, so producing vowels. We tracked the formants. We used some engineering approach for that, so no machine learning here. And then we did some machine learning, and in this case it was vector quantization, which just means we did some clustering, okay? And this is how the approach looks like. So first of all, we make all these observations. This is like a data cloud. And then we initialize our cluster centers based off of like the reference population. This is where the vowels should be for the reference population of mainstream American English speakers. So here are our cardinal vowels, and here's a couple of more vowels that are observed in this space. But now we need to adapt this to our data cloud here. So these are the reference population reference points, but for this individual there's something going on here, so maybe this vowel is actually here for this individual, right? It still sounds like that vowel, but it's not really at the location where the general population's vowel is at. And so this is what happens if you do some machine learning or some vector quantization. So one of the centroids moved up here and took over that space. This guy moved a little bit. This guy moved inwards because there's a lot of observations in the middle. And so this individual has this personal vowel space. So the green triangle is referencing to the individual's vowel space, while the red one is the reference population. And this is done, again, with unsupervised machine learning. In this case, it was k-means clustering. We're going to talk about how k-means clustering works in one of our lectures. So this is how the valid spaces look like for individuals that are not depressed. They are very large. They're almost overlapping with the reference population, but the reference populations one is a little larger. It probably is because they were asked to enunciate those vowels in isolation rather than in a conversation. But then if we do this for individuals that suffer from depression, we suddenly see that these vowel spaces are contracted, and they're much smaller than the vowel space that you observe for an individual that is not depressed. So there are a lot of observations here in the middle that are actually not related to any of the vowels that you would expect. So this individual sounds more slurred and like mumbled in their voice, okay? So this is one of the things that you can do with unsupervised machine learning. And so we learned these really low-level representations of acoustic features just with some k-means clustering, okay? And we found that there's a significant difference between depressed and non-depressed individuals. We found the same thing, or the same trend, to be present for another data set that we didn't record ourselves. So that's a German data set instead of an English data set. So there's a trend here happening, but it's not exactly the same. And I think the difference is because it's conversational versus read speech. So the data is recorded in a different context. In one context, people were asked to read a passage, this is here, and in this context, they were in a conversation. The same trend holds for PTSD, and it also kind of works for suicidal and non-suicidal individuals in a third data set that we looked at. It's kind of like a nice thing to see this work also covered in The Economist, where the author there wrote that what we're trying to do is to quantify behavior that was previously like a qualitative observation, and that we're trying to improve the knowledge of clinicians and try to quantify behaviors in these contexts. Are there questions about this? Okay, so I have to catch a plane and I need to leave earlier today, but I will post the homework this afternoon from the airport, and it's only going to be like read up a little bit on the articles that I'm going to post, and try to find some resources on machine learning, like data sets, challenges, toolboxes, etc. And I would like to reserve like 1 hour on Wednesday next week, where we can have like an open discussion, and maybe you could take some notes or have some questions that you would like to ask the rest of the class, or ask me about some things that you would like to have discussed in the course. I'll also put up, or maybe Lishing, you can do that, put up like a general discussion board on Blackboard. I think there should be a discussion board already where we can make a general question thread there where you can ask questions. And I think students also like this Piazza thing. We haven't set up one yet, but maybe if you could look into that, if there's some demand on that, so we can have some open question answer going on online as well. All right, great. So see you guys next week. Enjoy the long weekend.